So today we're gonna go a little bit further on the basic building blocks of the neural networks. We talked about, for example, what is a neuron, how the neurons are connected, what kind of mathematical function those neurons execute, and how we connect those neurons to make the neural networks more complex and increasing the hidden layer size, increasing the number of neurons per layer, and increasing the number of layers to add width and depth to the neural network. But we have seen before that those neurons, they're basically linear models. If you're familiar with classic algebra or linear regression, this is basically a linear equation where you have a certain type of model weight or the slope of a line, a linear regression line, for example, multiplied by inputs and then summed by the intercept. Or in this case of neural networks, we call it bias. So if we're looking at this definition of what is the kind of mathematical computation that a neuron is doing, it's basically just a simple linear model. We see that many neurons connected, they add complexity, they add width to the layers by adding more neurons in a layer, and we can add depth to the neural network by adding more layers. But the neurons alone, they are just linear models. So if we have only neurons in a neural network, the neural network, it will represent complexity, but it will still only model linear associations. So what really gives nonlinearity to the neural networks are the activation functions. So the activation function is an extra computation, an additional computation that is applied to the results of to the outputs of the neurons. For example, I'm showing here one layer of two neurons, and then these two neurons, each one is connected to all the inputs in the input layer, the x1 and x2. We apply that linear equation here, but before we send these outputs, this linear equation outputs to neuron 3, we have an intermediate computation here. We apply a function to these outputs. And that function applied individually for each neuron, it's not fully connected here, it's just for that particular neuron, is called an activation function. So in very simple terms, the activation function works like in the biological neurons activations. It decides whether a neuron is activated or not, but it's a bit more complex than that. It's more like a continuous signal that comes out from this activation. It's not just on or off. So basically you can think of an activation process like being an additional layer on top of that neuron layer that we have been talking about. You basically have an intermediate layer between this neuron layer and the next neuron layer. So there's this processing layer or activation layer. So there are different activation function types. So activation function can be any type of equation applied on top of those neuron outputs after you apply the linear calculations on the inputs using the model weights. Let me see. There's a question. So each activation layer has the same functions or different? So that's a good question. You can make a combination of different activations. Let me go to the previous slide. All the activations in this layer, in the same layer, they are usually the same. You could try to make some lower level implementation and try to modify the activation of each neuron, but I never seen anybody doing that. Usually the activations that belong to the same activation layer, they're all the same. So you choose one type and you stick to that in that layer. But then if you have an additional layer here, let's suppose that this had 3 hidden layers instead of 2. You could have another activation layer here that had a different type of activation. So that is totally flexible in neural networks. And actually, I have used that a lot. For example, if you have very deep neural networks, you use one type of activation for the hidden layers, but then in the last hidden layer, you use a different type, like ReLU versus sigmoid. I'll get into that. So there are different types of activations, and each activation function will return a different range of outputs. It will react differently to the same input data. The first basic type is if, for example, the activation just copies the outputs from the neurons. So that's basically using no activation at all. So if you just keep a linear activation, you still have a linear model. So the most interesting ones are the non-linear ones. For example, one very common activation is a tangent H or TANH, where you apply a formula that makes your results range non-linearly from -1 to 1. So this is one example. I've seen this using many neural networks that are not so deep, for example, 3 to 4 layers. This is a very common type of activation. There is also the sigmoid activation that applies a little bit different equation that makes your results range from 0 to 1. This sigmoid activation is very typical when you have dichotomous or binomial response variable. Then people usually apply this activation in the last hidden layer. So then the output, the predicted response of your neural network will be already ranging from 0 to 1. And then later you can convert those continuous values into probabilities of ground truth class, for example, probability of cases versus controls. So the sigmoid is very useful when you need a binomial or dichotomous predicted value. The next one is the ReLU, rectified linear unit function. It's a little bit different. It goes actually from 0. It's always zeroed out until it starts to go increase linear until infinity. So this kind of large range activation, it may look simple, but it can represent complex outputs and very fine signal. So people usually apply this function to neural networks that have a very big depth. For example, they have dozens or even hundreds of hidden layers, because this large range helps to preserve the signal all the way from the input layer through the hidden layers until reaching the output layer. And these are just a few simple examples. There are other variations of each one of these functions. There are other different types of activation functions, but those 3 ones, the tangent H, the sigmoid, and the rectified linear unit, are the most common ones applied to artificial neural networks. And they basically are the functions that give the nonlinearity to artificial neural networks. So I think so there are a few requirements for being an activation function. You could really create your own function if you want. Some people do that. They take one of these functions and they modify the equation a little bit. So you can do that as long as your activation function remains differentiable. So it's continuous. It doesn't have any jumps here or kinks that disrupt this continuity of the values. And this continuity is what allows the values, the training process to backpropagate the model error in order to improve the model performance later. And of course, they must be nonlinear, because if you apply a linear function, basically you're gonna keep your neural network linear. And the objective of an activation function is to give nonlinearity to the artificial neural network. So it doesn't make sense to make a linear activation.